Okay, welcome everyone. Welcome to our joint webinar for the Royal Society of South Africa and the Academy of Science. I should have taken out the okay, I should have taken out the automatic rollover. But just while we wait, I'll just let it run through. So we've got we've got a nice bunch of new fellows, which is really nice. And here they are being listed. And you can see they come from many places in South Africa, which is really good. Both universities and medical schools and hospitals. So that's really nice. And then we've also got, it's going to give me some new members, which are now on the screen. And this is also really nice. And we've got a student member, which is really great. And I think it's important that we have all sorts of levels. And this is just a bit about the RSSAf. Can read it. And this is a very useful organization. Okay, and future talks. Again, joint talks. The next one is me. And then there's the first one in 2025 that we've got. So the talk we're going to have tonight is from Professor David Dodoo-Arhin, and he's from Ghana. Here's some benefits for membership. That and it's gone past. Love it. It's a good organisation that puts you in contact with people. There is an online journal, and there's a chance to get some awards. And we also get other benefits through the RSSAf. So I'm just going to let this run once more. In fact, maybe, yeah, and then I think we'll start. But it's really nice. We've got some new members, and we also have some awards that we're going to be giving soon by the end of this month. So that's really nice. So we've got 3 speakers for next year. Right. So this is our presentation for tonight, and I'm going to stop the sharing. And if Professor Dodoo-Arhin can put up his first slide, then I'll introduce him. Okay, so our speaker, he's a professor of material science and engineering, and he's director of the Institute of Applied Science and Technology, which is an institute of the University of Ghana, which is a linkage for transfer of knowledge, technology, and innovation developed at the university to industry and communities. He's got a PhD in materials engineering from the University of Trento, Italy. He joined the Department of Materials Science and Engineering at the University of Ghana in 2011, and he's worked himself up to becoming professor in 2021. He's been the head of department for 2 years. He was acting director of this institute that he's now director of. And his research interest is in hybrid and nanostructured materials for energy, environmental applications, and waste to energy valorization. He's undertaken various postdoctoral research fellowships and visits at the universities of Pretoria, Cambridge, Strathclyde, Poitiers, BAM in Germany. And so he's done the groundwork, as we say. He's the chairman of the local organising committee for the 2025 International Union of Materials Research Societies International Conference on Advanced Materials, and that's going to be held in Ghana. And he's a fellow of the African Science Leadership Programme. He's served on many committees. He's got 109 peer-reviewed journal publications, 7 book chapters, and a patent. He's got an H-index of 31, and he's doing really well. What he hasn't mentioned there is we worked together on a thing called AMSEN, which was African Materials Science and Engineering Network, and he's also part of the Arua Centre of Excellence in Materials, Energy and Nanotechnology. So I'd really like to thank him for being prepared to give a presentation today, and hand over to him. Thank you very much.
Thank you very much, Prof. Prof. Cornish. Lovely to see you again, and it's lovely to be here. And I'm happy to note that you are currently the president of the Royal Society of South Africa, and also the chairperson for today's lecture. I would like to acknowledge also the members of council of the Royal Society of South Africa, also the fellows who have joined us and members who are on, as well as partners and collaborators who have joined this talk. Also our distinguished guests, some of the staff from the University of Ghana and also in Pretoria. We have some of our students who have joined us today. Then also we have some cherished alumni who are following us from the AMSEN days down to this time, as well as those in the Arua Centers of Excellence and the Clusters of Excellence. And ladies and gentlemen, I'm most grateful to all of you. Good evening, good afternoon, and good night to people, some of the colleagues joining us as far as in China and some in Korea. It could be morning, afternoon, evening, wherever that you are. Thank you very much for your warm welcome on to this presentation. But before I begin my lecture, well, I would like to acknowledge how grateful I am, especially to everyone and the Royal Society of South Africa. And I'm glad to be on this big platform, which is the South Africa's premier multidisciplinary scientific organization, and opportunity to deliver this online webinar. I'm truly humbled to hear all those nice things being said about myself. Sometimes I wonder if I am the one that we are talking about, but I'm so grateful to everyone that is here today. So for those who have never been to Ghana before, this is an overview of our country, Ghana. Ghana is in West Africa, and we don't only do academics. When you come, you can do a couple of things, and you can do sightseeing, and we have all various things that you can do here. I'm from the University of Ghana. University of Ghana was established in 1948, and then it became officially the University of Ghana in 1961. It started at the University of the Gold Coast, and it's currently based in Accra. We have over 66,000 undergraduate students and over 9,000 graduate students, and well, about 738 international students. And the faculty and staff close to a little over 6,000. We operate a college system of about 4 colleges. Prof also mentioned about the upcoming conference that will be held in Ghana, and I am the host. I'm doing that with our team in collaboration with the African Material Research Society, the International Union of Material Research Societies, and this is going to happen next year from 7th to 12th of December. So this is a wonderful opportunity for us to meet and interact in material science and engineering. Well, going on to the lecture for today, what I'm going to do is to start with some preliminary or some introductions, Then I will provide some context to my journey in sustainable materials in material science and engineering that will go beyond the limits. I will then revisit the conceptual foundations that make a case for symbiotic relationship between material science and engineering and sustainability, and especially looking at the humanities' basic needs. Therefore, I will also share some applications of sustainable materials that we apply in the basic humanities needs. I will also do some highlights on some of my research activities in this particular area, especially in the areas of advanced materials, in sustainable energy materials, and environmental solutions materials. I will then share some thoughts on some of the roles of sustainable engineering solutions in economic development, and we can look at it in a localized context. Particularly, going on, this lecture is looking at some resilience beyond a certain limit and combining that with sustainability. This key term, beyond the limits and humanity's basic needs, tend to be a highlight of today's lecture, which particularly will spark some attention because of the term beyond the limit and humanity's basic needs. Well, from my profile, my academic journey has been one that has yielded several insights that has taken me beyond limits. And these insights have proven applicable in different forms, which is intertwined between the nexus of material science and engineering and also in sustainability. But also, this is resonated throughout my personal and professional life, which I'm going to share with all of us. Beyond the limits actually means a determination and willingness to step outside one's comfort zone, to break free from self-imposed limitation or those that are inherent in one's physical ability. Oftentimes, these barriers are invisible, such as the fear of failure or even the fear of heights. Right, but going beyond the limit and sustainability, how are these related? Madam Chair, Prof. Cornish, at the beginning of the 1970s, a group of researchers published a report for the Club of Rome, and this was titled The Limits to Growth, as it is on my left-hand side, as shown here. And in this report, they predicted that a time will come when industrial production would completely cease, and the air, the land, and sea will be irreversibly contaminated. The study forecasted also a future in which the relentless march of the Industrial Revolution, environmental destruction, and unchecked linear growth of resource exploitation would all contribute to the impending catastrophe. But well, after 20 years later, a follow-up to this report that is on the right-hand side called Beyond the Limits was also published for the Club of Rome. The authors of this book argued that despite the overuse of many natural resources that are beyond their ability or replenish, and a disastrous future is not inescapable. It was also proposed that there will be two critical improvements to prevent this disaster. The first was through an overhaul of the laws and customs that support population expansion as well as material consumption. The second, as was seen, was to look at a sharp rise in efficient material consumption and usage. Thus, the implementation of these two improvements depends critically on the appropriate choice of materials and production technologies. This is very, very crucial, Madam Chair. Humanities, as we know, stands at a critical juncture facing an array of challenges that transcends geographical boundaries and temporary constraints. From climate change to resource scarcity, from social inequality to technological disruptions, or even the world that grapples with complexities that demand urgent attention and also innovative solutions. However, as engineers, scientists, and scholars, we are entrusted with a unique mandate. And what is this mandate? The mandate is to transcend the conventional boundaries of our disciplines and push the frontiers of knowledge and engineer sustainable solutions that address the diverse needs of humanity. Well, humanity has basic needs. We can take cues from Maslow's hierarchy of needs. And when we look at the hierarchy of needs as it's been shown here, we have the physiological, we have the safety needs, we have the belongingness, esteem needs, and self-actualization. So humanity's basic needs actually encompasses the essential physiological or psychological requirements for survival. According to Maslow's hierarchy of needs, as we have seen here, these physiological needs include the air that we breathe. As we can see here, we have sampled about 5 of these basic needs. And then these include the air that we breathe, the water that we drink. We think about also shelter. And it requires us to adopt a very, very holistic perspective that acknowledges the interconnectedness of all living things and the finite nature of our resources. Right. This brings us to the point where sustainability becomes a critical point in our studies. How then do we achieve sustainability? Achieving sustainability, as we can see from here, is not merely a technical challenge, as we always hear. It is really a moral imperative. It compels us to confront the inequalities that perpetuates the social injustice and the environmental degradation that we are observing on our planet today. These challenges, it challenges us to reimagine our systems. We have to reimagine our institutions in such ways that we can prioritize the well-being of both the present and the future generation. In the pursuit of social solutions, as well as sustainable solutions and their impact, we must definitely harness the power of interdisciplinary collaborations and collective actions. As we go on, we must leverage our expertise in fields such as engineering, in the fields such as science, in the fields such as policy, and in social sciences. Well, what we can also do is to cultivate a certain mindset, right? As we know that we need to cultivate this mindset that continuously learn, and then it helps us to adapt by reorganizing that the pursuit of sustainability is actually a journey rather than a destination. It requires us to embrace all the uncertainty, to experiment with novel approaches, and to learn from both success and failure. As we embark on this collective endeavor, I require us to draw on the inspirations that Albert Einstein gave us, saying, we cannot solve our problems with the same thinking we used when we created these problems. This means that we definitely have to think beyond the limits, and then we have to look at the conventional wisdom to challenge the status quo so that we can go beyond the limits in our challenges and in our rewards. And definitely the rewards are going to be very immeasurable. But what we think about is that in our approach, we can think about sustainability in the terms when safe drinking water will not be a luxury, but will be a fundamental right that is already available throughout and all over the world, which currently might not be the case. That we can also think about affordable and sustainable housing that becomes the norm, and also the build of these materials on the planet that can minimize the environmental impact. We also can think about sustainability in terms of agriculture, where we have this agriculture flourishing, ensuring that we can have our food security for various generations to come. In sustainability, we can also think about sanitation infrastructure that will also ensure that the health of the future of communities are really, really ensured. Meaning that together we have to embark on this journey that is beyond the limit of the way that we do things. We can arm ourselves with a resolve that we can move with a collaborative spirit and commit to a sustainable future. Now, this will bring us to how can we link our sustainability with the field of material science and engineering. So I'm going to provide some perspective to this in material science and engineering. So the field of material science and engineering, as we know, is a very interdisciplinary field. And this field explores the generation and application of knowledge that is related to the composition, the behavior. We also look at design, structure, and processing of materials to establish their properties and their uses. Well, this field also draws upon principles from chemistry. It also draws principles from physics and engineering that is used to address real-world challenges and relevant to technology, as well as it's also relevant to society and also our environment. Looking at this, we can find a certain link with climate change. We can also think about advanced manufacturing, renewable and sustainable energy, materials efficiency, as well as looking at it from the healthcare and even biotechnology aspects in material science and engineering. So this field has a lasting impact on the future global sustainability. If we look at it carefully, then the field of material science has no doubt that this engineering bit has sped and continue to lead the industrial revolution. With the fourth industrial revolution, material science and engineering can never be taken out. However, we need to understand that in the process of engineering, in the process of all these industrial revolutions that are occurring, it has led us to many problems. It has led us to many challenges. This includes the human exposure to many toxins, to rising demand for energy, water, and depletion of even our resources. Okay, this includes the pollution on landfill sites, a lot of the habitats that we are losing, and ultimately the impact on the global climate. So in recent times, there have been definitely improvements that have been made in terms of the environmental performance of energy, in terms of industry, as well as many sectors of various economies. However, there is still room for improvement, and this is where we come in as the field of material science and engineering. So it is very, very important to replace our traditional view of engineering with one that will focus on the sustainable engineering, meaning that sustainable engineering will integrate our classical principles of engineering into a new philosophical principle of sustainability. And that works together with the economy, that works together with our society, and that works together with our environment. Now, the concept of environment, social, the society, and governance has now become very prominent in our sustainability principles, no matter the field that we find ourselves in. And this principle is increasingly becoming relevant even in the field of material science and engineering, where we integrate the ESG principles in various projects, right? does include being very mindful of our material selection that we do. We are mindful of the energy efficiency when we do life cycle analysis, when we do recycling and circular economy. How then do we even operate with our workers and their safety? While what happens with our community engagement? How do we input these principles into that? Definitely, this is very important. And going forward, I'm going to share in this lecture some of the applications of sustainable materials in our work. And I'm going to show that in some of the works that I have done, including the fields of advanced materials, including sustainable energy, and also in environmental solutions materials. So we have done some work in terms of applications for shelter. We are still looking at the basic needs of humanity. We are linking our going beyond this limit where we are now incorporating sustainability into our shelter and to various applications. So we have also worked in the field of construction, looking at sustainability in construction. But we realize that shelter is one of the most basic and fundamental human needs that we cannot do away with. And in doing so, the development of very eco-friendly construction materials that will reduce environmental impact, that can also improve thermal efficiency of buildings, lowering energy consumption and cost, is crucial for sustainability, right? So when we bring in the traditional wisdom that we can fuse with modern innovation, this can now give rise to sustainable construction materials. And then these materials can minimize the environmental impact without compromising on the structural integrity of these materials. But we realize that in most of the construction industry, concrete is very, very, very important, and it's a relevant material that is used. However, concrete is a relevant contributor to global carbon emissions, and the largest part of its results from the use of cement, which actually acts as a binder in our concrete. And the cement alone is responsible for approximately about 10% of the global carbon emissions. Well, when we look at cement, each ton of cement will emit about 600 to 900 kilograms of carbon dioxide. And this is predominantly from the decomposition of calcium carbonate, but also from the energy demand, the processing, as well as the grinding principles, right? And therefore, it calls for more efficient use of our concrete in the future in order that we can reduce our cross sections, and then also the structural dimensions that help minimize overall materials that we will use. I mean, the material consumption is important here as we try to incorporate sustainability into our constructions. The most feasible way is to reduce the carbon emissions in concrete by replacing the Portland cement as much as possible with possibly a lower climate impact supplementary cementitious material, and also possibly use the cement as efficiently as possible. Well, we have done some work in various projects that we have done in collaboration with a team from BAM, which is the Federal Institute for Material Research and Testing in Germany. We've also done some work with MC Bauchemy, as well as various agricultural wastes that have been used and taking advantage of their pozzolanic properties, such as using of ashes from rice hulls, from cassava peels, also from palm kernel shells, or even coconut shells, have been explored in the various works that we have done here. What we found out is that they tend to show different degrees of pozzolanic activities, and then they can be used for different purposes and at different degrees, as much as about 25% as Portland cement replacement. Well, our study is also has also proposed some ways in which many biomass residues from agricultural waste, which hitherto are typically considered as waste, we can then create different processes, different non-competing value chains that can be related to how we even do construction in urban regions. So we have done a couple of works within this field. We have also looked at some applications of sustainability materials in terms of energy. How do we apply our sustainability in energy materials? Madam Chair, due to the rapid depletion and high consumption of fossil fuels and other natural resources, there has been an increase in the development and investigation of, say, renewable energies and clean energy conversion, as well as their storage technologies that can meet the present energy and consumption demands. Well, in order to make these efficient energy technologies, it is important to develop various performance, low cost, and even environmentally friendly conversion and storage technologies. And these ones have significant impact on alternative technologies that can be used to harvest various forms of energy. Well, as we know, this is a trend on the continent and in most developing countries, which Africa cannot be taken out. We typically are standing at a crossroads, which is a juncture where energy needs intersect with our commitment to sustainability. Well, in our part of the world, we call it doomsday, which translates to on and off, or what has now become known as load shedding, right? Which we are all facing this, and it's becoming a particular phenomenon across the continent. Well, this one is characterized by this frequent unpredictable power outages that is already affecting all of us. And it keeps on disrupting daily life. It affects our economic growth, and it is straining our infrastructure. So carbon materials have been found as one of the materials that can provide significant roles in alternative energy. And a typical one here is graphene, due to its various unique properties and various activities that we can get out of it. But we know that graphene, which is an allotrope of carbon, and it's a planar sheet of carbon atoms arranged in a network, can be used for various purposes. So as we see from here, this is graphene that we are showing here. Graphene is from graphite, and we can look at it in terms of a sheet of paper, which is made up of these various sheets. And these ones are coming in with various properties. And we can see they have properties in terms of transparency, in terms of conductivity, and then they are flexible, and they find themselves in very large applications and so many different areas. But we can produce this graphene in various forms. We can produce large-scale graphene using various techniques such as the chemical vapor deposition or even solution processing method that we are calling ultrasonic assisted liquid phase exfoliation. So our work has been in terms of exfoliating this graphene and producing ink out of it. And we have used these ones in the preparation of various inks that we can use for inkjet printing. So we find here, we can disperse our graphene in various solutions, depending on the whether it is organic solvent or it is polar solvents that we can use. We then disperse these ones and then generate inks out of it. So when we want to produce the inks, we can go on various ultrasonications, and we can collect the supernatant and continue on, and we come up with an ink that can be used for inkjet printing. But depending on the various viscosities that we want to get, we can add some additives to it, and then we come up with an ink. And this ink has been incorporated into an inkjet printing technique, where we are able to do printable surfaces. So here shows our inkjet printing technology, where the ink parameters, including the viscosity, the surface tensions, the nozzles dimensions, are taken into consideration when we are producing our ink. So here is the ink technology. We take into consideration a cartridge. This one is from an Epson, and we can look at this cartridge, and the cartridge has a certain nozzle side that the ink will have to drop in. So we take all this into consideration when we are doing the exfoliation, to be able to have particle flake sizes that are small enough to go through this nozzle, and then taking into consideration all these parameters that we can use for various printing. And then this can be controlled by using certain solid contents, solvents, and then some additives. When we want to do the printing, we look at the printability of the ink that has been done. When we have this phenomenon, which we can use a camera to observe this under the nozzle, in this situation, we have unstable oil droplet that you can have coffee rings are resulting from this. And when we have this, then at this final point, we have a very stable ink before we do our printing. So here is a typical example of a printing that is being done. This was done in collaboration with the Cambridge Graphene Center, and we can print on various surfaces. Right. So we can print on flexible surfaces. We can print on glass. We can print on different shapes. We did apply this in technologies such as the printing of dye-sensitized solar cells. And then these have been exploited in our inks using various functional methods that have been used. So here is the work that we did using dye-sensitized solar cells and using dyes from various plants that were used. And then in this situation, we demonstrated that low cost and environmentally friendly alternatives for the two key parameters of dye-sensitized solar cells. So the plant extracts have been used as photosensitizers here in place of ruthenium-based dyes, where the simple extraction procedure and a widely availability of all these ones were taken advantage of. Of course, the inkjet printed graphenes were also used as the counter electrodes for our work. And really, overall, the low material cost for this graphene electrodes makes them highly attractive for development of low-cost dye-sensitized solar cells. So this also brings us to the other part of our environmental solutions perspective. So here, what we do, waste management is a global challenge affecting everyone on the continent. So what we have done here is to look at the effect of plastics. And plastics are extremely important classes of materials that are prevalent in all the facets of society. However, this is creating a lot of problems. Although they are currently becoming a burden, the plastic waste is potentially untapped feedstock for various chemical and manufacturing applications. We find out that these have a lot of challenges that we see across the world. And it is estimated in Ghana typically that the manufacturing sector alone uses about 2.6 million metric tons of raw plastics annually. And this will lead to well over 1 million tons of annual plastic waste that is generated. However, when we look at it, approximately only 9.5% of that is collected for recycling, and the rest is led up to the landfill sites, or it gets into the sea, or it is openly burnt. And then these ones have their own challenges. Some of the techniques that can be used in the recovery includes the recycling, the reuse, or even incineration and energy recovery. And these have been identified as main techniques that can be used in downstream waste management. However, we have to think about the sustainability implications of plastic waste management and how we can valorize these ones in addressing the menace that is not yet fully understood. Well, from the front of Ghana, we have different stakeholders that are involved, including our Ministry of Environment, Science, Technology, and Innovation coming up. Also, the Ghana National Plastic Action Partnership is also aiding in support of this, as well as some of the United Nations bodies. But exponential growth in industry, as well as the population growth, is bringing up a certain demand, which is mostly petroleum-based fuel that are used. These are on the increase. Well, coupled with the usual experience of our increasing trends in the world prices of crude oil, the resultant search for alternative energies is inevitable. And these ones have now become a resource instead of considering them as waste. So we think that we can convert these plastics into fuel, in a project that is called the plastic waste to fuel valorization. So what we have done on our part is, through the support of the Embassy of France in Ghana, a proof of concept was made called this debris in, energy out, by adding value to single-use plastics. We have resorted to finding some remedy to this menace of the plastic waste by reprocessing these plastics into high-value fuels and chemicals that we are targeting households or even small running engines. And this project utilizes a locally and scientifically proven circular catalytic pyrolysis technique that is used in the setup for the conversion of these plastics. Well, we are looking at waste recycling and then also valorizing. So our target here is to convert these ones into fuel. So pyrolysis, in our sense that we are using, refers to the process of converting these plastics into solid components or liquid or even gaseous fuels using the heat to break down long-chain polymers into less complex molecules in the absence of oxygen. And this is what we have demonstrated in here. Well, we have done some preliminary studies. Some students have already worked on it. And then this have been done through the use of batch pyrolysis techniques to convert these plastics into various forms of fuel. And generally, we have done all these demonstrations and even have applied these ones into real vehicles to make all these demonstrations possible. So these petrol-like and we are getting diesel-like fuels are helping to solve some of the problems that the plastic waste is already engaging. So here are some of the real-time vehicular demonstrations that we have done here at our university. And we also look at the life cycle analysis, and then these ones have a lot of potential to be used today. So we are thinking of optimizing the processes of the plastic pyrolysis that can also help communities. Based on this, we further on have engaged communities to bring up this technology closer to the ocean and closer to our people. And then following this success, we have gone on, and based on our engagement, we have gone on to do a project that is called the Plastic Waste to Fuel Community Impact Project, which is currently running, that we are having some training of some of the youths in this particular area for the conversion of these plastics into the various forms of fuel. This is a really collaborative effort, and this collaborative technology transfer and skill development training aims at developing the vocational training and entrepreneurship opportunities for about 50 unemployed youth through the implementation of a pilot scheme that is focused on the recycling of these plastics using the locally developed pyrolysis technology. And these ones are producing low-cost fuels under a very sustainable, energy efficient, and environmentally friendly conditions. And we know that this project that we are embarking on, as we can see from here, we see this looking at the launch of the Valoplastic project that was done early part of the year. And then we have a demonstration of the process that we have here, as we can see in this video, the plastics that have been converted into fuel, and these ones are being collected, and these will be given to the fisher folks to help us reduce the impact of these plastics on the ocean. And this project is sited very close to the beach. So it is envisioned that we can scale up this project to other coastal communities to deal with both the land and marine plastics in a very holistic and innovative way. So what are our final considerations, Madam Chair? Well, as I wrap up this lecture, I put myself into this journey as we have been on this together, Madam Chair. It's my personal journey in material science and engineering, and much of this is looking at the basic needs as we fulfill our ups and downs that we go through and fulfilling our roles in sustainability. Well, in shaping our future, what I think is that our focus should lie in mentoring the young people, our younger generation, by helping these young generations have meaningful impact in material science and engineering, as we have demonstrated here. I think that by empowering these young ones and guiding them, we can create a generation of material scientists and engineers that are dedicated to advocating for Africa's sustainability priorities, right? And I believe also that this mentorship will be the cornerstone of fostering a culture of responsibility and innovation among future leaders. So looking ahead, we recognize the parallels between material science and engineering and the intricacies of sustainable development, appreciating the passion, the commitment, investment, capacity building, policy visibility, and the bright future that defines our field of material science and engineering. So in closing, I am reminded of the fact that what Marie Curie said, nothing in life is to be feared. It is only to be understood. Let us embrace the spirit of fearless understanding, emboldened by the knowledge that our pursuits in science are inseparable from our responsibilities to society. Let us all strive to be not just scholars, but also advocates for a more equitable and a sustainable world. I thank you all for your attention, and I acknowledge the support of my collaborators and funders. Thank you for your attention.
Thank you very much for a very interesting and meaningful presentation. I love the way you set the environment and of your talk and why it's so important and why we need to look at that. And I also like the way that you showed your work in a field that's highly relevant and highly useful. So yes, I think this is a really good project. And I think what I'd like to do, although I've got some questions, if we can, if you can get rid of, take off your presentation, please, then I can see if hands are up. Thank you. And because I don't want to hog talking to you all the time. I want to give other people a chance. So if there are any questions or comments, please can people put their hands up? I can't see any. Maybe I'm not seeing you. So if
There's,
somebody has got
Lumbani
okay,
and Benjamin Tommy.
okay. Please can Lombani go first and then Benjamin Tommy go next? Because I can't see them. Thank you.
You are muted.
Okay. Are you able to hear me?
Yes, now.
Okay. Thank you so much. Of course, I just joined the presentation on the midpoint, but still, it's so much interesting in the first place. And mine is just some two questions pertaining to the presentation and whatever has been even presented. And it's so much interesting, and I really like it. But my concern now is on the pyrolysis part, where you were presenting about how we can even process the waste, the plastic waste, into the biofuel. So I'm just stuck in the jungle, and I just want to be clarified on how do you weigh about the input energy and the output energy harvested after the pyrolysis process? Because I understand that to have that biofuel, there is a need of energy that should be put into the system, so that at least we should be able to heat the plastic waste into a certain temperature, so that we should be able to generate the biofuel. So mine is just a question on how do you weigh about the input energy and the output energy harvested after the process. Thank you.
Thank you very much. Yes, that's correct. In the pyrolysis process, definitely there's an energy input. Usually we operate within temperatures of about 300 to 400 degrees Celsius, and that process is required to be able to convert the plastics into the various forms of the fuels that you can get. This includes your liquid fuel, and then also some gaseous fuels that will be done. So in this our work, normally we do what they call the energy balance to see how much energy has been used, and then what we are getting out of it to be able to do the various calculations of the energy balance that we put in. Typically, we are not using electricity because we are doing it in a rural setting, sort of a rural community, and then trying to do something that it's a more low cost. We tend to use gas, which is burnt. So we know how much gas that has been expended for the period of time. Averagely, for about 25 kilograms, we are spending close to about an hour for the process to be completed. And then we can tell how much we have used and how much gas we are also getting. So the process also gives us some gas that we can also collect. And looking at it from a circular perspective, we're able to collect our gas, we can compress the gas, and it gets to a point we can reuse our gas. And then you can make all those balances to see the efficiency of the process. But the key point here is trying to find some other solutions to the plastic menace. How I described it earlier, it's a huge problem. And the project is occurring on the beach, where a lot of these plastic waste are entering into our ocean that has its own challenges with marine debris and all those ones. And it gets to a point where people even collect the fisher folks go to sea, and then instead of catching fish, they are catching more plastics. So it becomes an incentive to convert these ones and give it back to them as the fuel for their motors for the ocean. So there are all those balances, but obviously there is the energy part that has to be considered.
Okay, thank you so much.
Okay, you're welcome.
Thank you very much for that question and for the answer. Rafia, I think yours is the next hand up. Lombani, can you take your hand down now your question has been answered, please?
Okay, thank you.
Hello. Good afternoon, everyone. My name is Rafia. Yeah, thank you very much for the lecture, Prof. Dodoo. From what I take is I figured out you presented waste to energy. By waste to energy being the plastic into fuel to be used locally or in various different industrial waste. With regards to the graphene, when that one comes to being, what exactly is the graphene? If I admit myself not listening to you that well, what solution is the graphene coming in to take care of as an environmental sustainable measure?
Okay.
It,
I think it's clearer. So there are two questions in one, but I'll answer them for you. So the graphene is actually from carbon. So when I was talking about it, I mentioned that it is carbon. Carbon is conductive, and when we look at the carbon, it's a bulk material, and then we can look at it from the atomic level that we are calling graphene. That is why I showed it as a book. So graphite is carbon, and we can peel it off just like we are opening a book. So the graphene is just the sheets within your book. And these ones have a lot of properties at various levels. Material science and engineering gives us a lot of properties that we can take advantage of. So that is the point where we talk about the graphene. However, in our processes with the plastics, think of it that the plastics are actually hydrocarbons, and then they have a big carbon backbone. So usually when we finish the pyrolysis process, you have what we call the residue, and you have carbon that is generated. And these carbons, you can still have some level of graphene in. What we have done is to take some of these carbon materials that we have obtained and put them into energy storage because of the conductivity properties that they have. So we can take the residue, which is waste, and then we are putting it into a battery technology or into a supercapacitor for energy storage, which that part I didn't talk about it because of time. So this is where their linkages come in. So we can still do the peeling off and then doing the inkjet printing, which is just one of the things that we can do in terms of the energy storage principles. So that's where our graphene actually comes in. So we think of it that it is still a carbon material that we can use. Normally, we get this carbon from the plastic waste. We can activate them and get activated carbon. Okay, and this activated carbon can still be used for energy storage and other purposes like water filtration. And but in terms of energy, these are the areas that can be done.
right. Does the term cradle to cradle sound okay with the use of graphene to continue the process again, right from plastic to the carbon as a char, and then it being used in the production of printing materials, as you rightly stated. Am I right? Does the term cradle to cradle
the term cradle to
cradle?
Well,
not cradle to grave.
Well, I'm trying to understand the point, but then the part is that you can actually make these inks using these carbon materials. That you can use the graphene, you can even use the activated ones and use it for that. So the cradle to whatever that you are saying is not clear to me, but they are all usable. Yeah.
Right. Okay. I'm very okay with that. Thank you.
Okay.
Thank you very much for that. Sorry, Benjamin, Tommy, I sort of lost your I lost your hand. So if you can unmute and ask your question, please. Thank you.
All right. Thank you so much. Prof, I sincerely appreciate the presentation thus far. The paper is quite rich and indeed very innovative. Just a few questions. The first one is, though I actually joined late, and I wish I joined earlier before now, at least to have a good grasp of the entire presentation. But notwithstanding, let me just be very snappy. I noticed that at the course of the collection of the waste materials, particularly the plastic, I really want to understand, how did you carry out the waste isolation, considering the vast different waste aggregates that we are actually in the ocean? And then secondly, what are some of the limitations and challenges you probably encounter at the course of doing this project? And what other areas can you possibly recommend for scholars in the field to consider probably for future research work in order to enhance the efficiency and the sustainability quality of the products?
Okay,
Thank you.
Thank you very much, Tommy. Well, the issue of segregation, especially in our part of the world, is really big, because most cases people do not segregate the waste at source. So people don't separate the waste from the home and all those ones. So in the collection, you have to definitely do the various sorting out of the waste. So in our case, because we were doing it for academic purposes and then doing the transfer, it was important for us to segregate each of the waste and use the various type of plastics, and then to get the resultant effect. We, in our work, for instance, did not use, say, PVC because of the chloride content. So they have been, in terms of the polyethylene terephthalate, or what we call the PET bottles, the ethylenes, and even there are other ones that have been done in terms of the car tires. In all these ones, you need to collect them. We have to do some cleaning, and then some drying, and then shredding before we go through the process of the conversion. Usually, if you do not do the cleaning properly, then it tends to affect the properties of the product that you are going to get. For instance, the type of fuels that you can obtain has some effect if the segregation are not properly done. But also depends on the applications that you are going to use these ones. So for refuse-derived fuels, depending on the grade, then the segregation becomes not too important, but it is important to do the segregation. And this is a huge burden. Scaling it up, factories have to do complete washing, and then complete cleaning, complete segregation, which also brings up some additional costs. So these are some challenges and some of the limitations. So you still find that if we get to a point where we can segregate our waste at source, then the waste management systems become even more efficient. This is just one means of converting these plastic waste into fuels. There are other means that various stakeholders in the value chain are considering. In the road sector, others are adding it into bitumen. Others are adding even into building. Others are converting these various plastics into various other forms. What we are thinking is, how then do we take out all these plastics completely from the ecosystem? The plastic waste, we know that is not going to stop, but then we need to do something around it. Obviously, a lot of research is now going towards the use of biodegradable plastics, which will become very important. But currently, that part is still a bit slow, and we still have a lot in the system that are non-biodegradable. So we need to find better solutions that it will not be only recycling, but we can add value to it, and then we can take it out of the ecosystem completely. So I think with this, the limitations have been sorted, and then possible areas that can be considered by researchers has been done. But we need to really work with communities to expand on this, because there are a lot of things that are not only in our laboratories. We need to get out into the communities and solve real problems that is affecting all of us, especially what is going into the ocean. And now it affects everyone. It's a global village. Thank you.
Thank you for that question. Yeah, thank you for that question and answer. Yes, that's definitely a good thing to go into the communities. There's quite a lot of work going on in South Africa where waste is collected before, as you put your dustbins out on dustbin collection day. Some people, well, we sort our rubbish into things that we know are recyclable and things that are not. And other people come and collect it for dustbins. The dustbin vehicle comes and then they take it away, and then they make a living out of that, and it does get recycled, gets collected elsewhere and recycled, and that is paper, plastics and metals. So that's really good. Right, there's another question in the chat, and it's Yamikani Kala Lolo, sorry if I've mispronounced your name, which says, thank you for your presentation. I have a question on fuel from plastics. How do you determine quality of the fuel? In other words, can this fuel just be taken to be used in cars? Thank you.
Well, thank you very much for your question. So we do not just use the fuels. We have different grades, and we've worked mostly with our Ghana Standards Authority to do the various testing. But typically, one will run what we call the GCMS. So gas chromatography and mass spectrometer will give you some ranges as well as other values that we run. We run the octane numbers, the cetane numbers, and things like that. Then we can find the range in which we believe the product that we have obtained will be. On a straight scale, we go through a process just like we do in the refinery. So we have like 2 or 3 collection chambers depending on the various cooling rates. And typically, the heavier molecules will condense faster than the lighter ones until we get a non-condensable. So typically, our first collection chamber, which is heavy molecules, are within the range of, say, diesel. And subsequent ones can go as the petrol grade, and then different forms that we do. But obviously, there are various tests that we do before giving it out. For those in the fishing communities, they are not using the vehicular standard fuel. So they also have a certain standard that we follow in getting what we call the premix fuel, which is a lower grade version. But definitely there are various tests that we do. So whatever product that we get and we are going to use for those purposes, the various tests are done, and there's a match with the fuel, and to see if sometimes there could be a blend. But the ones that we use actually on the vehicles on campus, we did a test, we did trials, and it actually worked on the vehicles. Thank you. But I want to emphasize here that this project is not towards vehicular use. Our concentration in this project is to go into smaller communities, into smaller running engines and things like that, especially those on the beaches for the mowers, for some small running engines. These are the targets that we are looking at, especially communities that are off-grid, that they do not have access to this power. We can incentivize them to collect this, convert it into other fuels that hitherto they would have gone to buy. And 2 ways, you are bringing entrepreneurship as well as cleaning the environment and thinking in a sustainable way. Thank you.
Thank you for that answer and for the question. Are there any more questions? I'd rather take from other people before I say something. To our speaker. Oh, is that a question coming up? No. To our speaker, you did at the beginning of your talk show how society is important, and you had a Venn diagram, and I can't remember what you had around it, but sustainability was in the middle.
Yeah.
In so much of this, I mean, we're both materials people. In so much of this, there is a component, a society component, which you've already mentioned. How do you get around things like we've got really high consumerism, and even if I look at, say, something like cell phones, okay, or computers, the way everything is designed these days, you can only keep a computer ideally for about 2 years, because otherwise it starts giving problems because of the software and everything. I think, I think in some of this we've got to try and slow down. Yes, we're trying to get bigger and more, but I think a lot of it is at the detriment to the environment. What's your take on this, please?
Yeah, I perfectly agree. That is why these days the ESGs, the environment, social, and governance structure, is becoming very prominent, especially when we have already affected our environment. So the initial line for the first industrial revolution that has happened until our current state has been something called a linear economy. So in a linear economy, you take the raw materials, you use it, and then there's a waste, and then you don't really care about the waste. But in sustainability and in the circular economy, we are thinking that we should take the raw materials, process them, use them, find something for afterlife of these products. So we have issues with electronic waste, for instance, from the description that you've given in terms of the mobile usage, mobile phones. Then we find that what can we do to these ones instead of just dropping them and letting them become waste? We can find reuse. We can dismantle the various components. We can take some of those ones out and see which one can be used for something else. In that case, we can reduce the environmental footprints of our production line. That is why these days we are moving towards firmly towards the circular economy. Thinking about even the materials that we are selecting for the production of these cell phones. Possibly can we incorporate materials that do not have a lot of environmental footprints? Can we have a reduction in, say, the battery systems that are being used? Can we use more sustainable materials than, say, cadmium that has some carcinogenic effect or that has environmental impact? And these are the thinkings that are going in that at the end of life, we can think about it. And then that makes the importance of life cycle analysis, okay, being very crucial in our work. So as material scientists, as engineers, we need to put these ones into perspective. So, and this is being driven across many economies, not only in the scientific field, even in business, this is becoming very important. So whatever that we are doing, whatever that we are using, we think about it. And I like this print in some emails that I see, that when you want to print, think about the environment. What are the impacts that are going to happen? And gradually can find some restorations to this. Climate change is real and the effects are being felt, and it's the responsibility of all of us to think through this and to make our planet very sustainable and efficient for the next generation as well. Thank you.
Thank you for that. Lumbani, can you please mute yourself, because there's some strange sounds coming occasionally. I'd just like to if people haven't looked at the chat, thanks. There's some No, you haven't muted yet. There's some comments in the chat. If you haven't
Okay.
looked, please have a look there. And
Okay.
um,
Someone says I'm a teacher.
if anybody's got any other questions, please put your hand up or put something in the chat.
Okay, so I see here I'm a teacher, a researcher from Tunisia, and I'm looking for collaborations with colleagues to work on innovative projects like energy, water, environment. Please contact me via email, and there's an email in the chat. Then I see Dr. John, assistant professor at the University of Jinan, China, working on building construction, cement, concrete, CSA, cement, LC3, looking to meet friends in this field for future collaborations. Thanks. It also has the email.
And the offer's taken up.
Yes. Okay. And I invite all colleagues to collaborate together in a research project. Okay. Then Vivienne, thank you, Prof. David. It's encouraging to see Africans working towards sustainable future. There is a lot of potential in Africa, and indeed material science is the bridge to achieve sustainability. I'm Vivienne Chumbe, a research scientist working on carbon capture, particularly direct air capture in Kenya, deploying novel materials that are suitable to remove carbon dioxide from the atmosphere to achieve net zero emissions. We can engage more through my email. The email is already provided. Then there's the name is not okay.
Next question was we've dealt with that.
Okay.
And then the other one was Moshen.
Okay. So we can produce fuel from plastics using thermal degradation, catalytic cracking, and gasification. Okay. Right.
That's everything. So unless there's any more questions, I'd like to thank the speaker again for a very interesting presentation and a very thought-provoking presentation, and thank everybody for attending, and hope to see you at the next one, or if not, the one after that. So